Consider one concrete example. In this case, we consider the following Haskell program where let binding let foo x equals to case x of pattern matching. In case x is an empty list, return empty list. In case x is a non-empty list, we pattern match against the list by binding the head to the variable h and the tail to the variable t, and then on the right hand side we return h cons with an empty list. And then we define another let binding variable y equals to a list is starting off with 1 plus 1 cons 2 divided by 0 cons empty list. And then finally in the in part we apply foo to y. So notice that in the example that, or in the rules that we learned early on, we don't have a rule for let that with multiple declaration. So for now we can treat this kind of multiple let binding is a shorthand of we have the secondary binding to be pushed into a nested let and in expression. And return derivation of the running example. For simplicity, we already rewrite our function variable let binding into a simple let binding where we, instead of writing x here, write x on the left hand side of the equal sign, we put lambda x as a right hand side of the definition of the variable foo here. So now we also rewrite the second binding y equals to the list into an inner let in expression by applying this trick that we mentioned in the last slides. So now this entire program is in the shape of a let expression, so we can apply the let rule and constructing a substitutions of foo with this lambda expression, and we're going to apply these substitutions to the body, which is the which is the in part of the let expressions, and eventually this expression will be replaced or will be substituted. So we have the following as a result: let y equals to 1 plus 1 cons 2 divided by 0 cons empty list in, and originally this is our foo, now has been substituted by the actual lambda expression definition and applied to y. Again, this expression is a let expression, so we apply the let rule and we create a substitutions that replace y by the list. So we have these expressions. So clearly this expression is a redex where the first sub-expression is already in a lambda abstraction form. We can now apply our beta reduction, which is our F1 rule, and we substitute the formal argument x by its actual argument, which is this list, and now we have the case expression is the next step for us to evaluate. And notice that the conditional expression here for the case expression is already in the weak normal form, because the top level we are exposing the cons, which is a beta constructor. We can apply the case 1 rule to search for on the right hand side the matching pattern that matches with these conditional expressions. And for example, because we know that we can only match this list, non-empty list, with the pattern h cons t because it's not empty, it's not an empty pattern. So by matching it, we construct a substitutions of about h and t, and we replace h by 1 plus 1 and t by 2 divided by 0 cons empty list. Now we apply this substitution to the right hand side of the pattern clause, which is h cons the empty list. Okay, this is actually the body of that particular pattern. Okay, so we apply this substitution over here and we get 1 plus 1 cons empty list, and we stop here because we have no further rule for now to reduce this data constructor expression. Notice that when you run the same program in JCI or JC and eventually you try to print out the value, the print statement actually forces the cons expression to be further evaluated because we have to print out the list. So therefore every single element in the list must be reduced to a ground value or a constant value. in order to be printable. So this will be eventually evaluated into 2.